All right, probability and statistics, day number 9, normal distributions. The normal distribution is the first of our continuous random variables. So we had discrete random variables, which consisted of, kind of your discrete with multiple possible outcomes, as well as binomial. Now, I did just lie to you. We also have the no, I didn't lie to you. I'm a good teacher. Okay. So the Poisson distribution is also a discrete random variable. The normal distribution, like I said, is the first of the continuous random variables. Now, how we denote a normal distribution is by taking some random variable x and denoting it this way, where our parameters are mu, which is the mean, and sigma squared, which is the variance. Okay, so for example, if x is normal with a mean of, 5 and a variance of 2, then we would see our normal curve, right, which would be bell-shaped, and our standard deviation would be square root of 2. So this would be 5 plus root 2. Our first standard deviation to the left of the mean would be 5 minus root 2, and so on. Now, we can standardize that normal curve, right, and turn this into a standard normal where we have a mean and variance of 0, 1. And we can do so by using this, right? Our x values in a non-standardized curve, right, where mu is 5 and the standard deviation is root 2, right, can be transformed into z values, right? And those z values, right, are our standardized normal distribution. Now, this idea of a probability density function that you see here, this is a function that would represent this curve with standard deviation root 2 and mu equal to 5. So this would be the function, and it's really weird, but we're not going to talk about that until day number 10. So probability density functions are coming up, and this curve, of course, would identify the outputs on the normal curve. All right, let's get into a few examples. Okay, the weight of apples follows a normal distribution with a mean of 45 grams and a standard deviation of 5 grams. Apples are rejected from sales if they are less than 10 or greater than 42. Find the probability that a randomly selected apple will weigh less than 5 grams. Okay, so what we do here is, these are calculator problems. So you typically won't do many normal distribution problems without a calculator unless they're somewhat basic. So in problem A, I should say, what I want to do is I'm going to do a normal, use your pen, normal CDF. CDF, and the reason for the CDF, of course, is less than 5 grams. Okay, if you're going less than a value, what you want to do is you want to put a lower bound followed by your upper bound. In this case, our upper bound is 5. If you need a lower bound, typically a good number to go with is -1,000, right, if you're not already given one. Okay, that'll take you far enough out to that left tail that there won't potentially be any error. Okay, and I want my mean. Okay, I want my mean, which is given, 45. And my standard deviation is actually asked for in your calculator. Okay, even though the distribution itself, right, so if this were the random variable x, normal, 45, and what we would have here would be 25, right, because that's the variance. We actually punch into our calculator the standard deviation. So I'll punch in a 5 there. Now, if you think about this, this is actually going to be really interesting because if our mean is 45 and I go all the way out, it looks like what ends up being 8 standard deviations out to 5. We're actually just looking for this area out here. And your calculator, it's so small that your calculator actually gives us, this was our mean and this was our standard deviation. Our calculator actually says it's 0. So really good problem. You're welcome. Okay, so part B says find the probability that a randomly selected apple is rejected. So our apples are rejected if they are less than 10 or greater than 42. So I'm going to do a normal CDF again. Normal CDF. Okay, and now my lower and upper are going to be the values that I'm given. So I'm going to be given 10. Anything less than 10 is rejected. Anything greater than 42 is rejected. Still same mean and same standard deviation. So let's see what we get here. We'll do a CDF. We'll go from 10 to 42. Same mean, same standard deviation. And it looks like the probability that a randomly selected apple is rejected, well actually, let's see what we get here. We get 0.274. No, I told a lie. This is the probability that an apple is not rejected. So sad apple. Lots of these apples are getting rejected. Okay, if I take 1 minus that, I get a 72.6% chance that the apples get rejected. Okay. Now we got a little conditional probability in part C. It says find the probability a randomly selected apple is rejected given it weighs less than 30 grams. Okay, so now what I want to think about is, okay, so probability in this case that X is rejected. So rejected given it's less than 30 would be less than 10. Oh, no, when is it rejected? Yes, less than 10 given that X is less than 30. So what that's actually going to end up being is the probability that X is less than 10 and less than 30, which is just probability that X is less than 10. That's the overlap of those two, divided by the probability that X is less than 30. So let's kind of identify 30 here. And let's identify 10. I don't know, this might not be small enough, but what I want to do is I want to take kind of this red space, that'll be a probability, divided by this blue space. All right, so this will be the blue space and the red space, and let's see what we get. All right, so the red will be a normal CDF, -1,000 up to 10, 45, and 5. The blue, very similar. Normal CDF, -1,000, 30, 45, 5. So given that the apple weighs less than 30 grams, what's the probability that it gets rejected? Okay, so -1,000 to 10 divided by the probability -1,000 to 30. Oh, it's really, really small. Okay, so the red probability is so dang small that this actually comes out to be, wow, I mean, like, really, really small. 9 zeros followed by a 956. Okay, so that's just a poor example, but you can at least see the format there. All right, let's continue on another slide. Alrighty, let's go. Given that X is normal with a mean of 9 and a mean of 5 and standard deviation of 3, right? So I know mu equals 5, variance equals 9, so standard deviation equals 3. State the mean and standard deviation. Done. Mean 5, standard deviation 3. Find the probability that x is less than 4. So I would do a normal CDF. And I would go from -1,000 to 4. Let's see, what would that be? 5 and 3. Let's see what the calculator spits out for us. And what do I have? 5 and 3 for the mean standard deviation. Okay, whatever it is we're trying to calculate, the probability of it happening is 0.69 or 369. Okay, now interesting part in part C. It says find the values of A and B such that the probability that x is less than A is 0.00 or 0.011. Probability that x is greater than or equal to B, 0.871. Okay, so consider this is actually an interesting concept. We're going to use this idea of inverse norm. Okay, and what inverse norm does is it takes a probability and turns it into a score. So, for example, I press second vars. I go to option 3. It says inverse norm. It asks you for the area. Okay, so the first input will be the area. In this case, we would say 0.011. It asks for the mean. Well, I know that the mean of this particular distribution is 5, and it asks for the standard deviation, which we know is 3. So what this is going to spit out for us, right, is what it's telling us is that if this is 5 and a standard deviation is 3, then it's saying that if this area right here is, what is that, 0.011, then what our answer will end up being is whatever A is, right? So this answer here will be A. 0.011, mu is 5, sigma is 3. This tells us that A is equal to -1.87. Okay, so it's kind of cool. It identifies that. Clearly that's not to scale, but that ends up finding us a z value, right? Okay, so another example here. If I want to know the probability that x is greater than or equal to b is 0.871, then what I could say is that the probability that x is less than b is equal to 1 minus 0.871. So that would be my new value that I'd plug in for the second part. So inverse norm. Okay, I would have I don't know what I'd have. Let's just write 1 minus 0.871. Okay, same mean, same standard deviation. Let's find out the value for that. Now, seeing that the probability of this will be larger than the previous, right? It's going to be larger than this, I would expect the value for B to be somewhere over here, right? Somewhere greater than -1.87. So let's see what we get. Inverse norm, 1 minus 0.871. Same mean and standard deviation. Wow, it ends up a lot different, showing just how far off my first sketch was, and I get, actually, let's go with 1.61. That should be a positive 1.61. Okay, so that's the use of inverse norm to find a z value on a non-standardized curve. All right, let's continue to the last problem here. All right, here we go. Let x be normal with a mean of mu and a variance of sigma squared, given that the probability that x is greater than 85 is equal to 0.05, and the probability that x is greater than 25 is 0.10, or 0.1. Let's find the mean and standard deviation. So let's start over here. Okay, so let's look at two curves, right? I got my non-standardized curve. Oops, that's way off. There's mu. Let's say that This here is 85. This looks somewhat proportional. And let's say that this area here, probability that x is greater than 85 is 0.05. Let's look at the same idea here on the standardized curve. Okay, and not a great sketch, but this would be the probability that z on the standardized curve is greater than, let's call this a, is equal to 0.05. Okay, so let's use an inverse norm to find the value of a, right? Let's figure out what that is. We're going to use inverse norm. Okay, and what we ask for is probability, mean, variance. So on the standardized curve, sorry, that should be a 0. On the standardized curve, I got mean variance, but variance in this case is going to be equal to the standard deviation. So let's see what that z value would be. 0.05, 0.1. Okay. Now, however, I got this totally flipped. I ended up getting, what I want to do here is actually, I goofed this up. This should be 0.95, right? Because this would find the kind of the complement here. It would find this area, right? So in essence, like if you had a 0.05, you'd be finding this a value, right? Which actually came out, this is actually not a bad idea to just kind of describe anyways. Negative 1.64. So then this a value would be symmetrical, which would be 1.64. So that's the difference between using 0.05 and 0.95. So this gives me 1.64. Okay, so I'm going to use for the first time this idea that z is equal to x minus mu over sigma. Okay, so z, I know, ends up equaling 1.64. And actually, I'm going to store, this wasn't exact, I'm going to store this value. So I'm going to press stow, alpha math. So I'm going to store it as a. So what did I do? I pressed this button, stow. And then I pressed alpha. And then I pressed a. And what that does is like it takes your previous answer and it stores it as a. So I stored this value as a. So a is now equal to like 1.64, 485, and a bunch of garbage after that. Okay, I know that x equals 85. I don't know mu and I don't know sigma. Okay, so I'm going to do the same thing on the other side for this probability. Okay, so I know the probability that x is greater than 25 is 0.1. I'm going to use an inverse norm. I'm going to go 0.9, 0, and 1, and I'm going to figure out what the z-score, or the z value will be. Okay, so let's do that. Inverse norm. 0.9, 0, 1. And I'm going to store this as b. Okay, so over here, if I use the same idea, okay, then z, oops, wow, way off. Okay, z ended up being 1.28155 and a bunch of garbage. X is 25. Mu is still the same value, so is sigma. Okay, so what I'm going to do is now I've got two equations, two unknowns. So I get 1.64 sigma is equal to 85 minus mu. And 1.28 sigma. Of course, I'm not actually going to use rounded values. 25 minus mu. And I can use a system of equations here to solve. Now, I'm going to leave that to you guys. I'm not going to give you the answer here. But I would, if I were you, put mu and sigma, both to 3 sig figs. Do not round until the very end. And that'll be it. That's normal distributions, guys. We'll see you in the next video.